Hey everyone, and welcome back to Central Physics Reviews. The topic of today's episode is energy, which carries with it a lot more conceptual nuance than any of the other topics we've talked about so far. And in part this is because there's a lot of baggage that comes with the word energy from its colloquial use in our everyday language. So instead of explaining energy conceptually from the beginning and then having the comment section flooded with you guys asking about how to account for the energy coming from your aura, or what about all the good vibes coming from this Bob Ross positive energy drink, what I'm actually going to do is start out more mathematically and build into the conceptual understanding of what we call energy in physics from there. And to motivate all of the math that we're about to do, I'm going to start by telling you about why physicists get so excited when we discover a conserved quantity, or in other words, a property of a system that remains constant as it evolves over time. So as an example of this, we derived in the last episode that Newton's third law actually leads to conservation of momentum. And what that means is if you have some system over here interacting with, let's say, some external object down here, and neither of those two things are interacting with anything else, so they're isolated in the world, then the sum of their momenta, the momentum vector of the system, plus the momentum vector of the external object, will always be a constant vector, meaning it won't change over time. Now, in the last episode, we didn't really spend too much time talking about why this was such an amazing fact, but let's go over a really quick example that shows us just how powerful the law of conservation of momentum can be. So let's take a bit of an archetypical example. Let's say we have some astronaut in outer space, and the only thing that he's interacting with, so the astronaut is our system, we want to track his position over time, and the only thing he's interacting with is, let's say, a little hammer in his hand. That's probably not how you draw a hammer, but that's okay, don't judge me. So the hammer is this external object, and just by knowing that the total momentum of the astronaut and the hammer is conserved over time, we can predict what will happen to our system, the astronaut, if he throws the hammer, right? So if at some later time we have an astronaut over here and a hammer moving this way, let's say he threw it at 10 meters per second, then if we know the masses of these objects, so let's say, for example, we have a 100-kilogram astronaut and a 1-kilogram hammer, then without even knowing all of the complex interactions that went into the astronaut throwing the hammer and the hammer exerting a backwards force on the astronaut, we can already predict what the velocity of the astronaut will be after the hammer is thrown. And we can do that just by writing out that the initial momentum of the system, which was just zero because nothing was moving, is the same as the final momentum of the system, which is the momentum of the astronaut, which is 100 kilograms times whatever the system's velocity is, whatever the astronaut's velocity vector is, plus 1 kilogram times the velocity of the hammer, which is 10 meters per second, let's say in the x direction. And so we can immediately conclude that the velocity of the astronaut, v_sys, is going to have to equal minus 0.1 meters per second in the x direction. And that's so that the first term on the right-hand side cancels out with the second one and allows the conservation of momentum equation to hold true. And so this is a super helpful shortcut that lets us completely ignore all of the complex interactions between the astronaut's muscles and his hand surface and the surface of the hammer and everything that goes on as that hammer is thrown, and just get an answer that relates what the system is doing at some later time to what it was doing initially. So now that you've seen how powerful the law of conservation of momentum is, you're probably inclined to ask, is there anything else about this system that we know has to be conserved over time? And perhaps you can be even bolder. You can say, if I know nothing about the external object that our system is interacting with, is there any property of just the system itself that's conserved over time? And in fact, the answer turns out to be yes. And it's not a particularly simple quantity that's conserved over time, but bear with me here as I write this down. So we start with something that resembles momentum with a factor of 1/2. So we have mass times velocity. Remember, these are all properties of the system. But then we actually square the velocity on this term, and we subtract the integral of all of the forces acting on our system with respect to the position of our system. And so we take the dot product between those forces and some infinitesimal change in position in order to do that integral. And because this integral is indefinite, you can basically think of it as the antiderivative of the force with respect to the position of our system. So again, this combination of terms is going to equal a constant over all time. So it's going to be conserved over time. Okay, so this conserved quantity seems a bit arbitrary, but first things first, let me prove to you that this quantity is really conserved over time. And we can do that by manipulating this integral a little bit. So if we write out that this is the integral of mass times acceleration, or dv dt, with respect to position, dx, then we can pull a little sleight of hand and equate this to the mass times the integral of dv dotted into the derivative dx dt. And because velocity and position are assumed to be some smooth, nicely behaved functions, it's perfectly fine to swap over that dt from a derivative of velocity over time to a derivative of position over time. And of course, what you'll notice is that dx dt is just the velocity itself. So really, we're equating this to the mass times the integral of dv, a small change in velocity, dotted into velocity. Now at this point, it's a little tempting to just say, oh, we have an integral of v dv, isn't that just v squared over 2? But because this is technically a dot product between a vector v and a vector dv, we should be a little bit more careful in what we say. And so if we want to be a little bit more thorough about that, one thing we can do is to rewrite this yet again, this time replacing dv with a times dt, right? So that's just a rewriting of the fact that acceleration is dv dt by definition. And so we can replace dv with a dt, and we're left with the integral of m times the integral of acceleration dotted into velocity, now multiplying dt. And now if you look at this a little bit, you'll recognize that the integrand is actually the derivative of v squared with respect to time, right? So if we take v squared and we want to differentiate it with respect to time, then we can rewrite v squared as v dot v. So we have the derivative of v dot v with respect to time. And then some calculus will tell you that this is twice the dot product of v and one copy of dv dt. Or in other words, this is just 2v dotted into a. And so when we're doing the integral of a dotted into v, which is the same as v dotted into a, this fact basically gives us the answer because integration is just the inverse of differentiation. In other words, we can rewrite this and say that the integral of a dot v is just 1/2 of v squared. And of course, since we're doing an indefinite integral, we're going to have to throw in a plus c, right? Some arbitrary constant will satisfy that indefinite integral. And so what you'll notice, if you plug our answer back into our original quantity up here, you'll find that we have 1/2 mv squared minus this integral, which is really minus 1/2 mv squared minus a constant of integration. And of course, the 1/2 mv squareds cancel, and so you're just left with minus c, which is, of course, constant over time. That's just some number. So in practice, what we've shown here is that I wasn't lying to you. This combination of 1/2 mv squared minus the integral of f dot dx, for whatever forces are acting on your system at any time, is going to remain constant as the state of your system evolves. And that combination is precisely what we call the energy of our system. So now that we've gone through all of this detailed math, and now that you believe that this abstract, arbitrary quantity is in fact conserved in a system as it evolves over time, let's go ahead and try to interpret what these quantities actually mean conceptually. So let's start out by considering these two different terms, colored in red and blue here, separately. The first term is obviously the simpler one, right? It depends only on the mass of your system and its speed, not about what it's interacting with or how strong those interactions are. And in this way, it's very similar to momentum, right? It gives you a kind of feeling of how fast your system is moving. But of course, it's different because there are two factors of velocity, and that makes this quantity a scalar rather than a vector, right? It doesn't tell you in which direction your system is moving. but still it has that connotation of speed and motion, and so we end up calling it the kinetic energy from the Greek word for motion, kinetikos. Now, on the other hand, the second term, which involves integrating your forces with respect to the position of your system, doesn't have as clear-cut of a definition because it can vary with what those forces and interactions actually are. Now, one scenario in which there is a bit of a clear-cut interpretation to this term is when your force is actually just a function, so I'll write F equals F of x, the position of your system. So if the value of the force depends only on where your system is located, then integrating it with respect to that position of your system will just give another function of your system's position, right? So the value of this term will depend only on where your system is located. And for that reason, if this is the case, then we call the whole term, including the minus sign, potential energy, right? Because just being in a certain position adds to this quantity and gives you the potential to start moving, because it's the sum of the kinetic and potential energies that remains constant. So if you have more potential energy in one position than another, then by moving to the new position, you reduce your potential energy, and therefore your kinetic energy has to increase, right? So this is how we typically interpret the conservation of energy in these systems. You have some total pool of energy, which includes kinetic energy from moving and potential energy from your position. And so just knowing where your system will be located is going to constrain what its velocity can be, because you know how fast it has to be moving to keep that total energy constant. Now, I want to emphasize that this kind of interpretation only works under this condition that we wrote down over here, where F is a function of the position of your object, right? And these are typically called conservative forces that act in this way. And it'll be helpful to actually go through a couple of really important examples. So the first thing we can talk about is gravity on the surface of the Earth, so on Earth. And we know that this force is going to be conservative because the value of the force vector, as we said in a previous episode, is just the mass of your system times the gravitational acceleration, which is 9.8 meters per second squared, in the minus y hat direction, meaning downward. So technically it doesn't depend on the position of your object, but the important part, what makes it conservative, is it doesn't depend on anything other than your position either, right? This force is basically a constant as long as you're on the surface of the Earth, so it falls into the category of conservative forces as well. Okay, so now it should be pretty straightforward to compute the potential energy that corresponds to this conservative force. And in particular, we just do the integral in blue, right? So we have the potential energy, V, equals minus the integral of the force, which is mg minus y hat, dotted into dx, right? And now this dx vector, if you want to think about it in a two-dimensional world, is basically represented by the components dx and dy, whereas the minus y hat unit vector that we wrote down is going to be 0 in the x direction and minus 1 in the y direction. And so when we take the dot product of these, what we'll find is that we get minus integral mg, and 0 times dx gives us 0, and minus 1 times dy gives us minus dy. So that's how we take the dot product. And of course the minus signs cancel out, and what we're left with is mgy plus a constant, right? Since we're doing an indefinite integral. And so now that we've calculated what the potential energy is corresponding to the gravitational interaction on the surface of the Earth, the law of conservation of energy can be reframed in a much more useful way. Now we can write down that whatever your system is doing, it has to satisfy the fact that 1/2 mv squared plus mgy equals a constant, right? The plus c can be absorbed into that constant if you bring it to the other side. And so now, if you know what your total energy is at some point in your system's trajectory, then at any other time, you can figure out, if you know your velocity, what your y-coordinate has to be, or if you know your y-coordinate, what your velocity has to be, because you have this constraint on their sum. So just like with conservation of momentum, this becomes really exponentially useful when you have systems that involve complicated forces that are going to be hard to keep track of manually. So for example here, if we get a little slide, and for our purposes, let's call it a frictionless slide, so we don't have any friction forces, we can put a little box on this slide and say that initially it has some height y, and it has velocity v equal to 0. And a question we can ask is, when the box is down here, and its height is now 0, and its velocity is unknown, what does that velocity have to be? Right? Without conservation of energy, you'd have to go through every infinitesimal displacement of this box along the slide and calculate the forces on the box at that point. Now, the gravitational force isn't hard to calculate. We know that it's mg in the minus y hat direction, but there's also a normal force that you have to account for on this slide. And at every position on the slide, the normal force is going to be different, and that's not necessarily going to be easy to keep track of. So how do we solve this problem with energies instead? Well, all we write down is that our initial energy, which is 0 kinetic energy and mgy potential energy, is equal to our final energy, which is 1/2 mv squared in the kinetic component and 0 in the potential component, because again, y equals 0 at the bottom of the slide. And you can solve this equation to find that the velocity v at the bottom of the slide is going to be 2gy all in a square root, without ever having to even think about the notion of a force. Now, some of you might be watching this and thinking, wait a minute, that force in the conservation of energy equation means the net force, right? It means the sum of all forces acting on our object, so why are we only considering gravity here if we know that the normal force is also contributing? And the answer is that in this particular system, the normal force is always acting perpendicular to the direction of motion of our object along the slide, right? Because the object is moving along the slide, and normal forces by definition point normal to it. So because of that orthogonality, when you dot those normal forces with dx, you actually get 0, and they don't contribute to that total energy. Let's look at one more example. If we think about spring forces, a completely different application, then we know from Hooke's law that the force on an object tied to a spring, right, if you have a mass oscillating on a spring, the restoring force is going to be minus k times the position of that object, where k is some number called the spring constant. And here again, you can see that this force is conservative because it depends just on the position of our object and nothing else. So we can associate with that force a potential energy. Right, so we have the potential energy equaling minus integral minus kx dotted into dx. And typically when you're doing springs, you can actually work with a one-dimensional system, right? Usually your spring doesn't oscillate in the x direction and the y direction at the same time. So we can call the direction of oscillation our x direction, and then these vectors actually just become numbers along that direction. So we can go ahead and erase those little vector signs. And what we're left with is the potential energy is equal to k times the integral of x dx, which, as anyone who's taken calculus will tell you, is 1/2 kx squared. And so whenever you're working with springs, a very useful equation to keep in mind is that the kinetic energy, 1/2 mv squared, plus the potential energy, 1/2 kx squared, is always going to equal a constant. In other words, that sum is never going to change as your mass oscillates back and forth along the spring. Okay, so this interpretation was fun to go through, but the truth is, it's actually the simplest case we've been considering when the force that you're dealing with is just a function of your system's position. And in a lot of cases, that's actually not going to be true. So let's see how we can interpret this conservation of energy equation in some of those cases. Okay, so the first thing that we'll discuss is what happens when the force acting on your system isn't just a function of the position of your system, but it's also a function of the position of whatever external object your system is interacting with. And a really common example of this kind of setup is gravity, right? Not just gravity on the surface of the Earth, but gravity more generally. And if you remember, the equation for the gravitational force that Newton derived was F equals g m system external over r squared. in the minus r hat direction. And the proper way to rewrite this in terms of the positions that we know is to say that it's g times m system, m external, divided by the magnitude of the difference of the position of your system minus the position of the external object squared. Right? So we take those difference in position vectors and then we figure out what the magnitude of that difference vector is, and that's r. And then of course the direction is going to be toward the external system, so we say the position of the external system minus the position of the system. But we want that to just be a direction, right? We want that to just be a unit vector, so we go ahead and divide that by its magnitude, right? The magnitude of x external minus x system, and that just gets us a vector pointing in the same direction as this difference in positions, but with magnitude 1. Okay, so we know it's true from the conservation of energy that 1/2 times the mass of the system times the velocity of the system squared minus the integral of this force dotted into dx system is going to equal a constant. And the problem that we run into is taking this integral now becomes a lot more difficult, because not only the position of the system, but also the position of the external object is free to change. And the way in which those two variables change is actually connected. So taking this integral is much less straightforward than in any of the examples we considered previously. So even though the conservation of energy applies to your system in particular, it's not straightforward to calculate as a function of your system's position what its potential energy will be. So in this case, energy conservation for your system itself is not going to be a very useful physical law. But we shouldn't give up, right? We know that the force is a very simple function of r, and so we can think about what happens if we try to maybe do something analogous to the law of conservation of energy for just your system. We can think about what happens if we try to take the integral of f dotted into not dx, where x is the position of your system, but actually dr, where r is the relative position of your system to the external object. Right? In other words, what happens when we take the integral of f dotted into dx system minus dx external? Well, we can separate this out into two integrals, right? And we get the integral of f dotted into dx system minus the integral of f dotted into dx external. And if we remember from our last episode that if F is the force on our system, minus F is the corresponding force that our system exerts on the external object by Newton's third law. So we can rewrite this as the integral of the force on our system dotted into dx system plus the integral of the force on the external object dotted into dx external. And by the same arguments that we did in our initial derivation, we can conclude that this first integral just gives us 1/2 m system v system squared plus a constant, and the second integral gives us 1/2 m external v external squared plus a constant. So I'll combine those constants into one big constant over here. And so really what this integral is telling us is that we can come up with a new equation for conservation of energy that says 1/2 of the mass of the system times the velocity of the system squared plus 1/2 times the mass of the external object times the velocity of the external object squared minus the integral of f dotted into dr, where r is their relative position, is also always going to equal a constant. Right? So this is a totally separate law of conservation of energy, and it can be interpreted in exactly the same way, right? This is the kinetic energy of the system plus the kinetic energy of the external object plus the potential energy of the system and external object together also equals a constant, right? And I say plus there because the potential energy typically includes that minus sign outside that integral. So this relationship is as true as the one we had before for just our system, but this one happens to be very practical to use with gravity because it includes integrating our force with respect to the relative position, not just with respect to the position of our system. So the takeaway here is that when we're talking about forces that depend on relative positions instead of just the position of the system of interest, then this is the law of conservation of energy that we want to be using instead of the first one, because this one will be easier to actually find what the potential energy is. And we can do that, right? Let's do that for the case of gravity. The potential energy of this whole thing, so system plus external object, is defined as minus the integral of f dotted into dr. And so that minus sign will cancel with the minus sign in the force. So what we're left with is just the integral of g times the mass of the system times the mass of the external object divided by r squared dr. So this time we're being a little sloppy, right? We're not treating this dot product very rigorously, but we saw before that this actually gives us the same answer as if we were careful with the dot product, so hopefully you'll forgive me for taking that shortcut. And of course, when we do this integral, we get that it's equal to minus g m system, m external, over r. So the equation that you want to keep in mind when you're doing energy conservation through a gravitational interaction is that the kinetic energy of one object plus the kinetic energy of the other object minus g m1 m2 over r is equal to a constant, or doesn't change over time. So these are the kinds of things you want to think about when your forces depend not just on the position of your system, but also on the position of what it's interacting with. And sure, even in the case of gravity on the surface of the Earth that we did before, that gravitational force does technically depend on the position of the Earth as well as your position, but in that case, the Earth is so heavy that its position can basically be taken to be constant, right? Even though you exert a force on it, you're not going to really be accelerating the Earth very much. So because of that, we can treat that system as though it only really depends on your position, because everything else is just a constant number. Okay, so all of the contexts that we've talked about so far involved conservative forces that either depended just on the position of our system or on the position of our system and some other position. But what happens in the case of non-conservative interactions? In other words, a force that isn't even a function of the position of our system? Well, it turns out that most interactions of this form are actually just contact forces. And these involve things like, of course, friction and air resistance, but also things that are more simple, like the normal forces that come in when you just bump into something else. Right? We talked about normal forces before in the case of our little gravitational slide, and in that case, in that context, the normal force was always perpendicular to our direction of motion, so it didn't play into energy conservation. But if you, throw a ball at a wall or something like that and it bounces back, then those normal forces are in fact in the direction of dx, and so those do play into energy conservation. So how do we interpret this blue energy contribution if we can't write down a potential energy for these interactions, right? If the force depends on more than just the position of your system, then it's hard to assign any meaning to some sort of arbitrary indefinite integral of f dot dx. But luckily, in the case of contact forces, there is another sensible interpretation of this blue term, and we can derive it just by looking at the math, right? So if we write down this integral, or I guess minus integral, of f dot dx, and we label it to be specific that this is the force on the system, and this is the change in position of the system, then we can always rewrite this as the positive integral of the force exerted on the external object times dx cis, right? Because Newton's third law tells us that those forces are equal and opposite. But if these two surfaces are in contact, then in that particular case, we can say that dx of the system is going to equal dx of the external object because they're moving together, they're in contact. And so this integral is really f external dotted into dx external, right? We can write that equivalently. And conservation of energy itself tells us that this integral is basically 1/2 m external v external squared. Up to a constant, we can write down minus constant. So in the case of objects that are interacting via contact forces, we can rewrite energy conservation by saying 1/2 m system v system squared plus 1/2 m external v external squared equals some new constant. And the obvious interpretation of this statement is that the sum of the kinetic energy of your system and the kinetic energy of whatever external object it's interacting with is always conserved. So if your system loses kinetic energy, that external object will gain kinetic energy. Or if that external object loses kinetic energy, that kinetic energy will go to your system. So just like before, we had a pool of total energy that included your system's potential energy and your system's kinetic energy. Now, in the case of contact forces, we can interpret this as a different pool of energy. Now it includes your system's kinetic energy and whatever external things it's interacting with kinetic energy as well. Now, there's one massive caveat that I have to mention here, which is that technically this derivation assumes that you have one point-like particle interacting with one other point-like particle. But most contact forces involve your system interacting with a whole bunch of different particles as it, say, travels across a surface and interacts through friction, right? And so what happens is that the kinetic energy that your system loses through friction is distributed independently to each of the different particles it can come in contact with. And those particles don't all have to start moving in the same direction, because remember, kinetic energy isn't a vector, it's just some number. So you can have one particle start moving up because it gained kinetic energy from your system, but another particle got kinetic energy from your system and started moving the other way. And a third particle started moving to the right. And so what you have to realize is if your system is interacting with an object made up of lots and lots of particles, then the fact that your system transfers its kinetic energy to the external object doesn't mean that that external object as a whole will now start coherently moving with that new kinetic energy it got. It could actually remain stationary while the particles inside it are just jiggling around in all different directions at a faster speed. And that jiggling is something we refer to as heat. Now, there will typically be some coherent motion of this external object that got kinetic energy of your system, so I kind of lied to you when I said it could be stationary. But the point is you shouldn't assume that all of the transferred kinetic energy goes into that coherent motion. And in fact, if you want to figure out just how fast that object will be moving as a whole, what you should really be doing is using conservation of momentum. So the right way to interpret this blue term, this kinetic energy of the external object, is really as a combination of things, right? It includes 1/2 m external VCm squared, right? The center of mass motion, or the overall motion of this external object, that's included in its kinetic energy. But it also includes the heat component, which we're not really going to try to quantify. But the real takeaway here is that if your system interacts with an external object through contact forces, its kinetic energy can be transferred to the external object by some combination of making that external object move as a whole and just heating it up. So if we want to make a little diagram of all of the different places the kinetic energy of our system can go, here's what it would look like, right? First we have the kinetic energy of our system. Then we have, well, it can definitely go to the potential energy of our system if there are any conservative forces that are interacting with the system, right? So if we integrate that conservative force, we get some potential energy. And if there are any contact forces, then we also have to consider the kinetic energy of the external object, or whatever's interacting through contact with our system, as well as the heat of that external object, which is usually given a variable Q. Okay, so these are the four kind of pools of energy that we have to consider whenever we're doing energy conservation. Now, in terms of energy transfers, we know that conservative forces are free to transfer energy between the kinetic and potential energies of our system. So we can draw arrows down and up and label that F conservative. And that's all that conservative forces do. Every other interaction or transfer of energy is going to be from contact forces. So for example, contact forces can take the kinetic energy of a system to the kinetic energy of an external object. So I'll label that F contact. Or the other way around. If you have coherent kinetic energy in an external object, contact forces can bring it into your system. Similarly, a contact force can turn your system's kinetic energy into heat of the external object. So that's also a contact force. And some contact forces, like air resistance, can turn the potential energy of your system into heat of the external objects that it's interacting with, right? Like the air heats up when you drop an object and it hits terminal velocity. It's losing potential energy, but the air around it gets hotter. So that's also contact forces going from potential energy to heat. But until we get into thermodynamics and we start talking about engines and stuff like that, what you'll never have is heat turning into coherent energy of motion or coherent potential energy, because it's hard to get a bunch of randomly jiggling particles to all somehow bump into your system all in the same direction and make your system accelerate that way coherently, right? That's why we don't have any arrows going from heat to any other form of energy. And this little diagram basically sums up everything we mean by conservation of energy. If you add up all of the energy contained in these four little clouds, you're going to get a number that doesn't change over time. And so this is the mathematics behind the statement that energy can only be transferred from one form to another, but never created or destroyed. Now, the last thing I wanted to talk about is this idea of work and changes in kinetic energy. So if we go back to our energy conservation equation that we started from in the very beginning, right, 1/2 mv squared minus the integral of f dx is a constant, and we want to ask ourselves how our kinetic energy changes from one time to another, or from one point in the system's trajectory to some other point, then this equation can actually prove very helpful. And that's because we can relate the change in kinetic energy to the change in whatever the blue component of this equation is, whether it's potential energy or kinetic energy transferred to the external world, whatever it is, we can relate that change to our change in kinetic energy. And that's because if we look for a change in this side of the equation, right, we can always equate that to a change in the other side of the equation, because these two sides always have to be equal. And we know that a constant never changes over time. So the right-hand side is just going to be 0. Meanwhile, on the left-hand side, the first term is the change in kinetic energy, which is what we're trying to solve for. And the second term, right, we have to take minus the change in this indefinite integral of f dot dx, right? And so that whole sum is equal to 0. Now, those of you who are calculus savvy will know that the change in an indefinite integral from one position to another is just the definite integral between those positions. In other words, we can write delta k is equal to the definite integral from some initial position to some final position, I should really write these as vectors, of f dot dx between those positions. And this integral, where we take force and dot it into a little displacement and sum it up over a bunch of displacements over a trajectory, if we do that integral, then that's called the work, and that's given the variable w. That's the work that's done on our system, and you can notice that it's just equal to the change in kinetic energy of our system. And this statement is very informatively known as the work kinetic energy theorem. Now, other than just defining what work means, this equation actually gives a slightly different way to interpret conservation of energy. And in fact, what it says is that the change in your kinetic energy of a system will always equal this integral, which we know, if the forces are conservative, is just the opposite of the change in potential energy, right? So it's equal to minus delta V if the forces are conservative, right? If F is just a function of x, for example. Or, as we said before, if you have a contact force that isn't conservative, then this integral of f dot dx just represents the opposite of the change in kinetic energy of your external system. So this equation means that the change in kinetic energy of your system is equal to minus the change in kinetic energy of the external world if F is a contact force. And so this is an equivalent way of thinking about energy conservation, considering changes in energy canceling each other out, rather than the total energy being a conserved quantity. Those are two sides of the same exact coin. Okay, so this has been a particularly long video, so let's go ahead and summarize all of the key things that we talked about here. The first thing, and maybe the most important thing to realize, is that energy was the name we gave to some particular conserved quantity in mechanical systems. We didn't start with a concept of energy and try to force math onto it. It's a name we give to a mathematical quantity, right? It's this difference between 1/2 mv squared and the integral, the indefinite integral of f dot dx. That's just what we call energy. Then, for the purposes of our own human intuition, we didn't have to do this, but we chose to, we gave names to each of the two different components of this energy, right? The component that reads 1/2 mv squared we called kinetic energy, and the component that was minus integral of f dx we called potential energy in the case of conservative forces, or we realized that that was just the kinetic energy of the external world in the context of contact forces. And of course we went into the caveat that just because your external object or external world has kinetic energy doesn't mean it's moving as a whole. Part of that kinetic energy can just be the heat within that external object. Once we got all that nomenclature out of the way, we realized that if our interaction is a conservative force but depends not just on your object's position, but on its relative position to some other moving object, then it's most convenient not to consider the conservation of energy of just your system, but instead to look at conservation of energy between all of the interacting objects together. Once that nomenclature was out of the way, we realized that if our force was a conservative force, but it depended not just on our system's position, but also on the position of some external interacting object, then we could actually define a potential energy in a different way, right? Instead of doing minus integral of f dot dx, we could do minus integral of f dot dr, where r is the relative position between our system and the external object. And doing that integral showed us a new law of conservation of energy that applied to the system as a whole. If you add up the kinetic energies of not just our system of interest, but also the external body, and you sum it with this new version of potential energy, then you actually also get a new conserved quantity that is particularly useful in these cases. Finally, we realized that if we consider the definite integral of f dot dx instead of just the arbitrary indefinite integral or antiderivative of force, then that definite integral actually gives us the change in kinetic energy from whatever position you start that integral at to whatever position you end it. And that change in kinetic energy, or that integral in particular, is what we call work. And if your force is just a function of position, then this integral is really easy, right? You just find the indefinite integral and plug in those boundaries at the initial and final positions, right? You don't even need to know what path your system took. But if the force is non-conservative, if it's a contact force, then that approach is impossible because you can't just find the indefinite integral of your force dotted into dx. What you need to do is you need to do a path integral along the specific trajectory that your system traveled in. And that's why even if you start and end in the same position, like if you go in a circle, for example, you can still lose some kinetic energy to those non-conservative forces. Now, the few of you who stuck around to the very end of this episode get a special bonus fact. We just saw that in the Newtonian framework of classical physics, where each interaction corresponds to a particular force, energy is a pretty arbitrary quantity that turns out to be conserved over time as a system evolves. But as you go on to learn more advanced physics, you learn that there's something called the Lagrangian formalism and the Hamiltonian formalism, which are structures where interactions between systems instead correspond to a particular potential energy function. And in fact, you can derive trajectories of systems just by knowing that potential energy without ever talking about forces at all. Now, these frameworks of physics, where we talk in terms of energies instead of forces, are most natural when those potential energies can be easily interpreted, meaning when the forces at work are conservative and don't involve interactions of two large multi-particle systems. And that's precisely why these frameworks that speak in terms of energies instead of forces are used when we're talking about the most fundamental interactions in our universe that occur between just a small number of particles. So our most basic description of the universe, which comes in the form of quantum mechanics and quantum field theory, is written entirely in this sort of language without ever invoking the concept of a force. So keep in mind that while energy might seem really abstract and arbitrary in the context we've been working in, it's actually one of the most important quantities we can use to better understand the dynamics of the world we live in. So with that said, I hope these explanations have been helpful. And if you still have questions, hopefully ones that don't involve auras or Bob Ross, go ahead and leave them in the comments below. And hopefully I'll see you in the next episode.